Hi, this screencast is looking at intermolecular forces, and an intermolecular force is an attraction that is between two molecules but is not due to a bond. So we're going to look at the different types and some of their properties in this screencast. Intermolecular forces are when you have two molecules that are attracted to each other and they form almost like a bond, but it's not a bond. And some of the resulting characteristics are things like a boiling point or a melting point that is high or low, depending on how well they're attracted to the other molecules. There are three types of intermolecular forces. There is dipole-dipole, there's hydrogen bonding, and there's London dispersion. So we're going to look at each one of these types with more detail in the coming slides. All right, here is the first intermolecular force. This is called dipole-dipole, and a dipole is a molecule that does not have evenly distributed electrons. An example is the HCl. You can see that hydrogen has no electrons of its own, and chlorine has 6 electrons of its own, and then there's a pair shared in between. So a dipole is when you have an uneven distribution of electrons, and we can draw it with an arrow with a plus on one end, and the plus will go towards the more positive end and the arrow will point towards the more negative end. What is actually happening in this molecule is that the electrons are arranged unevenly and they are forming a polar molecule, meaning that there is an uneven sharing of these electrons. So the chlorine end of the HCl bond is more magnetically negative and the hydrogen end is more magnetically positive. So if you line them up like a bunch of magnets, they will cause an attraction just like a regular magnet. So a dipole-dipole force is strong. There is one that's stronger, but it's mostly strong, and it happens in polar molecules. Now that's the important part because you have to have an uneven distribution of electrons. If you have evenly distributed electrons, you do not have a dipole, and therefore you do not have this type of intermolecular force. Because there's uneven charges, you form dipoles, and then you have that opposite charges. So you would have a hydrogen, and in fact, I'm going to see if I can write this in pink so it's a little bit brighter. You have your hydrogen and chlorine, and this one has all these extra dots, and right beside it is another hydrogen chlorine in that beaker of the hydrochloric solution. So you have an attraction here between these two oppositely charged molecules, and they attract each other. As I showed you above, when you are drawing this, you will show it with an arrow with the positive end pointing at the positive end, or the less electrons, and you will do this for each bond in the molecule. As I said previously, the negative end of the polar molecule attracts itself to the positive end of the adjacent molecule, the nearest ones. So they can only attract to the one right beside it. This is called dipole-dipole attraction because you have two dipoles attracting each other. And this has to be in pretty close proximity. They need to be nearby. Our second type of intermolecular force is hydrogen bonding, and this one is the strongest. And this one is the reason why water behaves the way it does. The elements that can happen or can do a hydrogen bond are HF, HO, and HN. And there's a mnemonic you can phone home, and that will help you remember which elements are allowed to do this. The reason that this occurs is because the large electronegativity difference between hydrogen and F, O, and N. These all have very high electronegativities, and so therefore they have very uneven electrons. The intermolecular force in which a hydrogen atom is bonded is due, like I said, to the unshared pair electrons that are floating around the F, the O, and the N, and they are being attracted to the hydrogen. So if we look at water looks like this with a couple pair of electrons, and another water would be nearby. And so what would happen would be there would be an attraction here, and you'd actually have, I'm trying to draw the next one, you would have another one over here, and there would be more attraction, and you get this whole network formed between all these water molecules and these hydrogen bonds. And so you have incredible surface tension, or you have cohesiveness and adhesiveness, or great boiling point or melting point. All these characteristics of water are due to the hydrogen bonds. The hydrogen bonds are usually represented by the dotted lines that I just showed you. You will see them in between an unshared pair and the next atom. An example, as I said, is water molecules. And there is a lot of characteristics and unique properties in the why we can live the way we do as a result of the hydrogen bonding in water. Here's an image of what hydrogen bonding looks like within your glass of water. You can see the red dots and the blue dots. This is a water molecule. And so you have lots of water molecules. And then you have these dashed lines here, and they represent all the hydrogen bonds that are occurring. And you can see that they're all over the place. And that allows the water to have really strong attraction to each other. All right, our third intermolecular force is called London dispersion forces. And even noble gas atoms and nonpolar molecules can experience a very weak intermolecular force. What is happening in this one is that as your electrons rotate around your nucleus, you have your electron moving around, you sometimes will be near another molecule. And so periodically you will have a temporary uneven distribution of electrons. So this is completely temporary, and this is due to a dipole kind of like occurrence, in that your electrons are uneven, but only for a moment, and then they move around, and then it's not uneven. So you have an instant electron distribution that's uneven, and you can cause a small attraction. So if you're following along in the text that's on the screen, it says a temporary dipole can then induce a dipole in an adjacent atom or molecule, and the two are held together for an instant by a weak attraction between the temporary dipoles. So like I said, you have those, you have the electrons rotating around the nucleus, so you have that constant motion, and also you have a constant motion next door. So every now and then you're going to have a case where your dots, your electrons are near each other, and they, you will have a temporary opposite charge occurring, and therefore have a very weak force attracting each other.